All right, so last time we started our whirlwind tour of optimization methods with a focus on convex optimization. And today we're going to finish that up. Hopefully we'll get through all of this. We're going to continue talking about convex optimization first. So I'll define convex functions, or rather I'll expand upon the definition of convex functions, give some examples, talk about some ways to check if functions are convex or not. And then I'll give a bunch of examples of convex optimization problems and highlight one of the main important features of such problems, which is the fact that local optima and global optima are the same thing. If you have a point that looks good locally around some region around you, that actually is also a globally optimal point. That is really why we can solve these things efficiently. So I'll actually prove that in two slides here, in the slides. And then I'll talk briefly about non-convex optimization. So I'll talk about if problems aren't of this form, what can we do? And we're going to cover one of these forms in particular later on in the course called integer programs. But for now, I'll just kind of highlight the high-level techniques people use to actually solve these things, which are roughly divided into either local methods that find a local solution and global methods that find a global solution. And finally, I'll talk last about algorithms for actually now taking these problems and solving them. It's great to be able to write them. It's great to know that they can be efficiently solved, but how do you actually go about solving them? That's what I'll address last. So it's quite a lot to talk about today, but hopefully we'll get through it all. As always, interrupt me if you have questions, but we'll hopefully try to get through it to the end. If not, we can do a few minutes at the beginning of class next time. All right, so I defined the convex function last time, right? It is a function where if you take any 2 points in the function and draw a line between them, that line lies above or on the function itself. Okay? Now, when you want to test if a function is in fact convex, one thing you can do is just plug in the definition and see if it works or not. Right? You can just do that. That can actually be tricky sometimes. So there are a bunch of other conditions that people use in some cases. Some cases actually that can work fine. But some cases there are other conditions people use to verify whether or not a function is convex. The one that you may see most often of these conditions is a condition on the second derivatives of that function. So first let's talk about a one-dimensional function here. Ignore this bit here. It has some definitions here that look nasty, but they're really quite simple. So for a one-dimensional function like this, we want this function to always be kind of curved upwards, right? The function's ever not, even if it keeps going upwards, but it never keeps sort of curving upwards more and more, you can find a point here where it's not convex. So we need to be curving upwards. And what corresponds to sort of upward curvature for a scalar function is the condition that the second derivative of that function, the second derivative, the first derivative is the slope, so it's going to be the slope everywhere. The second derivative is how that slope is changing. That has to be positive everywhere. And if that's positive everywhere, the function has this positive curvature that's going to guarantee this property. You can't have this. It's going to guarantee this property that if you connect any 2 points, the line between those 2 points will lie above the function. So we're not going to prove that. It's not that hard to prove, really. But this is a very common condition on functions to prove that they are convex here. Now, that is for a function of a scalar value, right? A scalar input function. When you have functions that take vectors as inputs, and remember, we're still talking about real valued functions, so the functions will always still output a single real value. That's what we're talking about overall here. When we talk about convexity, functions always output a single number. These functions, at least. But for a function that takes a vector as input, we need another condition other than this, right? The normal kind of second derivative isn't really even that well defined. So what we have instead is an equivalent condition on this matrix here called the Hessian. So don't worry about this if you haven't seen it before too much. We're not going to make you sort of compute Hessians or do operations with Hessians here. I just want to get you an intuition of what the Hessian is and why it's important in this context. So the Hessian is a pretty simple function of a, well, it's a function of a function, I guess. or a matrix that's a function of a function. So we have a function f, which, as a function, so we have a function f, which, as before, maps vectors in Rn to real valued numbers. The Hessian, which we write like this. This is sort of this kind of derivative sign, type sign, with respect to x. Squared means it's the second derivative of f of x. This whole thing here is a matrix. It's a matrix that is n by n. And the ij column of this matrix, this equals the partial derivative, the second partial derivative of f of x with respect to xi and then xj. Okay, so we take sort of all possible second derivatives of that function with respect to all xi's and all xj's. And of course, the diagonal entries then are the second derivatives of this function with respect to xi squared, with respect to xi twice. Okay? Now, the equivalent condition for positivity of the second derivative in the scalar case is a different property of the Hessian matrix. Okay, so this Hessian matrix, in order for a vector input function to be convex, this Hessian matrix here has to be what's called positive semi-definite. Okay, so we're not going to, again, this is, I'm introducing another term here, which also might be confusing if you haven't seen it before, but it's actually really quite simple. A general matrix A is positive semi-definite, and we're going to write that as this little kind of squiggly greater than or equal to sign. This is true if x transpose AX is greater than or equal to 0 for all x. Okay, and this is kind of an equivalent condition to positivity, right? Because if this was a scalar number, then of course these would now just be scalars, and so a times x squared is greater than 0 if and only if a is greater than 0 for all x, right? And so the equivalent condition for a matrix is that this thing has to hold for all vectors x. If this property holds for this matrix of second derivatives, the function's convex. Now, actually proving this, you can actually prove this in a number of ways. We won't go into it because we're not going to talk here about proving things are convex. I will tell you certain things are convex, and you can use those rules. But we're not going to worry too much about kind of breaking down matrices and determining if they're positive semi-definite or not. But one simple condition for this is that if A, and in fact this is actually any semi-definite matrix can be written like this, but it isn't always obvious that it can be. If A can be written as some matrix B times B transpose, then we know A is positive semi-definite. And the reason is pretty simple. It's saying that, okay, so if A is equal to this, then this thing over here would be equal to, maybe I'll write it like this. It doesn't really matter. It's B transpose B or B transpose. It's the same thing. This would be equal to X transpose B transpose B X, which would be equal to Y transpose Y for some other vector Y, namely B times X. And this thing here is always positive, right? This is the sum of the squared entries of Y, and it's always positive. So that's one way you can prove this. But again, we're not going to worry too much about these kind of things for this course here. It's just, this is the definition of, or rather, this is a condition for convexity. It's very useful sometimes. All right, so let's mention some examples now. I'm not going to sort of go through all these in detail. They're really in the notes so that you know them all, or in the slides so that you know them all. And they're useful in some cases, some are less useful in other cases. So for example, the exponential is a convex function. And you can prove that by just taking the second derivative, and you'll see that it's a squared. The exponential of a times x for any a. Second derivative is going to be a squared times x to that, and that's always greater than 0. So simple. A can be positive or negative here. The negative log of x, that's also convex. And actually, I should write more as convex for x greater than 0. It's undefined. We're not worried about complex values here. It's going to be undefined for us for x less than 0. less than or equal to. Actually, equal to, it's negative infinity, so that's fine. But for less than 0, we're not going to be defined. The squared Euclidean distance. So this function here, f of x equals x transpose x. That's the one we mentioned over there as well. You've seen it in a few places. We also will write that sometimes as this thing, y transpose y. This is, without the square there, that's called the 2 norm of y. It's essentially the Euclidean distance, or the sort of Euclidean length of the vector y. And squared, it's just going to be equal to y transpose y. So we'll see that kind of function a lot. That one's also convex, and the best way to, that one's actually a little trickier to show directly from the laws of convexity, that sort of showing that the thing always lies above the line. But it's very easy to show the condition on the Hessian holds here. If you just do the math, and you can do it sort of, all in terms of scalar values, what you'll find is that the Hessian is equal to the identity for this matrix, for this function here, which is a positive definite matrix. Euclidean distance. So even without the square, this is actually also convex. This one's much harder to show. Essentially, it follows from properties of distance functions, like the triangle inequality for distance functions corresponds very quickly to the direct properties of convexity. This is an important one here. If we have a set of convex functions, then their sum, their weighted sum, as long as these weights are positive, is also a convex function. Right, so you can add up convex functions and they're still convex. As long as you're adding, not subtracting them. You can't subtract the convex function, then it's the opposite, it's concave. A few more. Negative square root for x being greater than or equal to 0. That's convex. Or equivalently, the square root is concave. This is kind of a fun one here. It's a function called log sum x. So it's actually, if you take a vector, take every element in that vector, e to that element, add them all together, and take the log of that, that's convex. We won't prove that. That one you can prove by looking at the Hessian. It's a nasty kind of longer expression where you actually will want to do some matrix calculus to figure that out, but it's not too bad. It's kind of one of these examples of fun functions that actually do come up sometimes in practice that is in fact convex. Another kind of important general rule. So these are all sort of examples, but there's the one we had before of like non-negative weighted sums. That's kind of a general rule. Another general rule is if you have a bunch of convex functions and take the maximum of those functions, meaning you take of all these ones, you take whichever one has the biggest value. So for example, if you had a bunch of linear functions, which we know are convex because they're affine, or rather affine functions, which are all like lines, right? Doesn't really matter what I draw here. Okay, so if we take this function and take the maximum value of the maximum function at every point, that would be this thing here. And that maximum is a convex function. Similarly, actually compose convex functions with other functions. And the rules are actually a little bit more general than this, but a simple rule is that if you have some function f of y, which is convex in y, then you can take an affine transformation of some other variable x, like ax minus b. F of ax minus b is also convex in x. All right, so you can put essentially linear things inside a convex function, and the function's still convex. So all these rules together are actually quite powerful in terms of the type of functions you can prove are convex. There's one other thing. Oh yeah, there's a question there. No, so this is just a function of, this is any linear form here. In fact, A doesn't have to be square even, right? So A is a arbitrary matrix here. This is an affine function of x. Now, one other property which I'm just going to mention here, which is sort of relating convex functions and convex sets, is that the for f being a convex function, something called the sub-level set, which is the set of all x such that this function is less than some constant. I guess you should maybe like put the constant below there or something like that to indicate what it is. But anyway, this set here is a convex set. Okay, so that means that this, this is now, if you take any 2 points in the sub-level set, then and draw a line between them, those points will also all lie in the sub-level set. And that follows it sort of right away from the functional definition of convexity, right? Because you have some function, you have some line here, that's C. You take 2 points that are below. We know from convexity that that line's going to lie above the function. So therefore, the actual function value has to lie below this one for all of them. And all these simple properties, they seem simple, but they're actually really quite powerful. All right, so let's test how well those all sunk in. I will leave these up if anyone wants me to go back to them. And this will also be this will actually also be the last these quizzes for today at least. We're not going to have any more. But here is a quiz. Here are some functions. I made it a little bigger this time. Oh no, I made it bigger, but I also made these choices. So that's not very good. So let me fix that. Okay. Oops. Yeah. Did I actually create it there? No. You can start reading these things. Let me just do this. This is poll. I want to allow multiple choices. And visible later. Okay, post my poll. All right, no, that's it. Okay, so now I'm going to publish it. Of course, when I publish it, it seems to hide the actual equations. Okay, there we go. All right. Piazza, I guess, is still working out there some of their kinks. Okay, so now it's all set up. Here are 5 functions, and I want you to tell me if they are convex or not. You can use all the rules from the previous one. If anyone wants me to go back to one of the slides, I can go back. But tell me if you think they are convex or not. It is open now, right? So you can start voting. Okay. So we'll give like 5 minutes or so. Can people see this a little better than last time? I tried to make the text a little bit bigger, so I think it should be a little more visible than it was last time. Does anyone want me to flip back slides? Okay. Tell me how far you want me to flip back. The notes are on the website too. If you really have computers, you can download them and look at them separately. But the question, go back to the question now, okay. That'll take me a second because I have the wrong, well, these are the right things, but these are the old poll. I should also mention the size of all these the x's here. It is actually implied by the equations that I use, but I will say it what they are in case there's any confusion. Here, these two, x is a scalar value. And you know that because I'm writing x squared. And I would never dare to write x squared if x was not a scalar value. If it was a vector, it would be uninterpretable what that means. Here, s can be a matrix. It doesn't have to be. It can be a scalar, but it's, or sorry, a vector. In this one, x is a vector. It can be a scalar too. It actually does not affect whether it's convex or not, whether it's a vector or a scalar. But x can be a vector here. These two, x is both a scalar. So x is a scalar for all of them except this one, where x can be a vector. But if you treat x as a scalar, actually it won't hurt you in this one either. Anyone want me to go back to more slides still, or that'd be helpful? Sure? Okay. This one before too? This one's good? Okay. All right, I'm going to go back to the questions now. Everyone got their fill of this slide? Okay. $35, we're getting up there. We'll get till 55. So getting some answers then again. The most important part is just to answer the question, not to get it right. Students naturally want to get them right, so it's actually an amazing, even if it counted for no credit, I think people will still try to get the answers right. So, oops, I scrolled down a bit.
Last time. So yeah, how hard it is. Well, I got it. Well, I got it.
All right, so it's 55. If you haven't submitted yet, just submit whatever your current checks are in the next 10 seconds. All right, good. And I'm closing it. Okay, let's see what people said. Oops, show the results. Okay, so interesting. All right, This is great to talk about. Okay, so the first one, almost everyone said correctly, that is a convex function. It is, right? 1, this constant value 1 is a convex function. It's a pretty boring one, but it's a convex function. Certainly evaluate as many points as you want. It's going to lie on that line. X is a convex function. Is affine, in fact. That's a convex function. And x squared is convex. We know that both just by looking at it. It's pretty obvious that it is convex. Second derivative, if you want. Second derivative is 1. It's a convex function. It's also the same as the Euclidean norm in 1D. Or sorry, the squared Euclidean norm in 1D. They're all convex. The max of that is convex. The second one is not convex. Okay? And the reason for that is that, actually, no, sorry, the second one is convex. It normally isn't. Sorry, it normally isn't. But the fact that this always dominates that makes it convex, right? So negative x squared is always negative, and 1 is positive, right? Well, 1 is always bigger than that, and negative x, that's fine. That's affine, so everything is good. So essentially, it looks like this one. 1 positive, and then it goes up when after this starts being no, the other way. Sorry, the other way. Right? This way. Okay. Looks like that. This third one here is also convex. The third one here is a max of 0 and an affine function. Affine is convex. The max of, therefore, and the max of convex functions is convex, so the max of 0 and this is still convex, and the sum of all of them is still convex. Okay? So this is actually does anyone know what this is? Has anyone heard of what this function here is? Does anyone want to say? Okay, so this is what's called a support vector machine. This is all it is. So if you've heard that term before in machine learning, it's this right here. There's one more term to it, but this is pretty much a support vector machine. This one here, people were right. This one is convex. It's 2 exponentials. Those are both convex. The sum of them is convex. And finally, this one here is not convex. This would look like the max of 0 and x would look like this. The square root of that, rather, would look like this. I'm overlapping my lines there, so. It would look like this. And there are obviously points here where the function is not above. The line would be below the function. So this was a kind of a tricky one here. It was. I even got tricked up by it, I guess, right, when I was saying the answers. But other than that, I think people did very well here. So this one might be a little tricky too because it's composition of multiple things, but it is convex too. All the rules from the previous slide apply to it. Okay. Let's keep going. Last quiz. That's the last quiz for the day. Now you can just sit back, zone out, I guess, right? Don't have to listen to anything more. It'll be on the homework though. So. Okay. So now, having said all that, using the sub-level set property. Remember, I've sort of been switching a little bit, and this has caused some confusion, I think, at the beginning, between writing the feasible region as some abstract set C and writing it as a bunch of functions that have to be less than some other thing. So hopefully this will make it clear why this problem is convex when these things are convex and these things are affine. So a convex optimization problem can be written like this always. Minimize over x, f of x, subject to a bunch of functions being less than or equal to 0 and a bunch of functions being equal to 0. This is a convex problem if and only if f is convex, all the g's are convex, and that ensures the feasible region is convex because the sub-level set of a convex function is a convex set, and the intersection of convex sets is a convex set. So you're basically saying that you have to be within all of these, each of which is a convex set. These functions here, the equality constraints, have to be affine. Remember, the only allowable equality constraint, I mean, for something to be essentially an equality constraint, it has to be both a inequality constraint in both directions, right? It has to be less than or equal to 0 and greater than or equal to 0. And the only functions that have that property while both being convex are affine functions. So the HIs here have to be affine for this region here to describe a convex set. And then to have a convex objective, f has to be convex. Now, the key property, or a key property of convex optimization problems is, as I mentioned before, all local solutions are also global solutions. I'll define what I mean by that a little bit more formally right now, and then prove this property, or at least the slides have a proof, and I'll talk about how that proof looks. Okay, so there's a lot of text in the slide, but it's actually quite simple. First of all, a point X is globally optimal. This is a very simple one. If and only if there's no feasible Y, if it has to be feasible, first of all, and that there's no feasible Y such that f of Y is strictly less than f of X. But that would mean there is a point that is also feasible, that has strictly lower objective value. That would make X not a optimal point. Now, a point is locally optimal if it has that same property, but that property only holds for all Y's that are within some distance of X. So a locally optimal point says that for any other feasible points within some distance of this point X, none of those points have f of Y less than f of X, or equivalently for all of them, f of X less than or equal to f of Y. Okay, so that's sort of very intuitive, right? Because locally just means if you look kind of around yourself, at some distance around yourself, you look good. And globally optimal means everywhere you're good. You're the best everywhere. I'm not worrying right now. I should also add, I'm sort of skipping over this. You can be a little bit more formal in terms of defining the domain of these functions, and you have to in some cases, but we're not going to worry about that. We'll just assume that we're sort of correctly defining the domain of these functions such that they're always going to be defined for the inputs we care about. Okay, now here's the theorem, and it's a probably 2 long line proof, maybe 5 lines in slide form. So the Therenin's property about convex problems is that any locally optimal point is also a globally optimal point. And what I mean by that is compare this to a problem like this, right? Where this is a non-convex function, and this point here, all the points around it in some range look good, right? It's better than all of them. But this is the global optimum of this function, right? So the property of convex problems is that this can't happen. And why is that true? Well, we're just going to prove this by contradiction. We're going to assume that there is some point y such that f of y is less than or equal to f of x. So we'll assume that x is not a global optima, but it is a local optima. Then we can pick this point. So this point here is a new point z that is some combination of x and y. It is, in fact, a convex combination of x and y. That's an important point here. Z is a convex combination of x and y using this particular value for theta. So it's this particular convex combination of x and y. All right, so the intuition here is we have, I'll draw it for this one, but basically we have points x and y. We assume that y is less than x. Naturally, I'm drawing a non-convex function for this to actually happen here. But we're going to pick some other point, z, that is actually close to x. So this is in the region close to x. And we'll show that it's feasible. And if convexity holds, which it doesn't here, but it will in that case, if convexity holds, f of z is also less than f of x. Okay, and that contradicts the local optimality of x. And really, that's all there is to the proof. The details then are just in the next slide, and they're just the math. So essentially, why do I pick that value, particular value for theta? Well, actually, there are 2 things here I should mention. The first is that f of z is less than f of x. That's the first thing you show. And f of z is also a feasible point. That's important too. We know immediately it's feasible because the feasible region for a convex problem is convex. So z of this form will also be a feasible point if x and y are both feasible.
What was the definition of feasible region?
Feasibility means it's in the feasible set. It satisfies all these equations here. So if it's true, then z is feasible, and I'll show you that z is going to be strictly less than x. Yeah.
How do you know that theta is not negative?
Okay, yeah, it's a good point. How do we know theta is not negative?
Because
Yeah.
x minus y of 2 is less than or equal to y, so that will be less than 1.
Well, that actually would make it a negative value, right? If it was, it's the point is that we're assuming x here is locally optimal, and if y was near x, that would be, I mean, we're assuming that y is a global optimum, that it's not within that range. So that means that this distance here is bigger than r, so this whole thing is less than 1. Actually, it's actually less than, yeah, it's between 0 and 1. And then if you just sub in the math here, essentially, what you do is you show the distance between x and z is, well, this big thing here. A lot of these terms cancel. You get this term here, which when you bring things out outside these norms here, a lot of things cancel, and you get this whole distance here is less than r. So don't worry about this here. This is just sort of algebra at this point. All right, and what that shows is that if this was the case, if it was possible, right, that we had an x that was locally optimal but not globally optimal, we can find a point z that is in the neighborhood around x that also has a value less than x, so x therefore cannot be locally optimal even. And that's all the proof. Okay, but there are really 2 points here. The point is that first of all, z is feasible, and second of all, z is actually has better objective. Z is within the local region of x and is a better objective than x does. So this is a really powerful property. Because what it means is just intuitively, if we just take some starting point for our optimization procedure and kind of just, in some sort of sense, make sort of local improvements, right? We take steps to make a little bit and a little bit better. If we can do that, then we will actually reach a point where we can't get any better by taking any steps. And we know that point is not just sort of a locally optimal solution, it's a globally optimal solution. Right? Yeah. How do you know when to stop? That's actually a really hard question. It depends on the problem. For certain generic forms of convex optimization, you can define what are called stopping criteria that essentially say you're pretty good. And we'll actually talk about that in a second, sort of for like an unconstrained case. We'll talk about kind of what looks like it's good. But then numerically, that's a hard question. I mean, even if mathematically you know the answer to that, and it's actually, you can enumerate mathematically what it means to be at a solution, but numerically a hard issue because you're not quite there. Should you go farther or not? And in fact, there's a huge, the analysis of algorithms for optimization focuses hugely, essentially, on how many steps you need to get how close to a solution. Okay, so that's the simple proof there. Now I want to run through a few examples of convex problems. Okay, so the first one was this least squares problem. Remember, I wrote least squares like this, or motivated it like this. You have a bunch of points, B's and A's, and you have a bunch of points here, and you want to draw a line through it that minimizes the sum of those errors, the squared errors between the point and the line. And the first term of x was the slope, second was the intercept. I'm going to write that in general like this. Minimize over x the squared norm of ax minus b. Now, first of all, why is that the same thing here? What that is saying is I have a matrix A with m rows and n columns, and I'm multiplying it by x. Okay, what that does is that takes this vector x and multiplies it by the first row of A. Takes the inner product of the first row of A and the vector x, subtracts off the first element of this vector b. That's ax minus b. That's another vector that has all those terms. Then you take the squared L2 norm of that, squared Euclidean distance, which is the sum of all those, the sum of all entries in this vector here squared. Okay, so for example, in our case where we before had the a's on the x-axis and the b's on the y-axis, what that would look like was that a here would really be a1 and then 1, a2 and then 1, down to am and then 1, times x1, x2, minus b, b1 down to bm. Right, because essentially to make this a intercept term, you always add it. So you always add, so this here would be a1 times x1 plus x2, oops, not equal to, but minus b, minus b1. Take all those terms together, you square them, that's the equivalent to sort of the figure I drew, or the equation I had on the first slide. This is just a more general form, because A can actually have more than just 2 columns here. It can have many columns. This is actually a multivariate least squares problem, it's called. Okay, so the optimization variable is x, and the data matrices are A and B. And this is a convex problem. Why is it convex? Actually, why is it convex? Yeah, this is an affine transform here of x, and we know that this squared L2 norm is also a convex function, so the whole thing's a convex function, and there's no constraints here. So it's an unconstrained convex problem. Our next example, this Weber point problem. Here we have AI, and I'm actually going to even say that let's just go ahead and treat these as n-dimensional points here. That's just 2-dimensional points. We minimize over x the sum from I equals 1 to m of x minus ai, where ai, each ai now is itself a vector in Rn here. This is a convex problem too. So why is this one convex? Needs one more step than the last one, but why is this a convex problem? Right, so each term here is convex. We know that's convex because we know that the Euclidean distance is convex. And this is the Euclidean distance of an affine function in x. So this thing here is an affine function of x. This thing, therefore, is also convex in x. And it's the sum of a bunch of those, which is therefore also convex in x. Okay, so we're really applying these rules a lot. And this is really how these things work, is that I almost never will check directly if a function, some function is convex. You'll be able to see it by applying these sort of rules from the last few slides. The general rules, like the max rule and the sum rule, these kind of things. And that's actually a much better way, oftentimes, of figuring out whether something is convex or not. Okay, so, and you could add constraints here too, as long as they're convex constraints, and this would still be a convex problem. It's going to be a little more generic now. And I'll talk about linear programming. Who here has heard of linear programming before, or has ever used linear programming? Those could be different. So a linear program, as I said before, linear programs were so popular at first that at first, optimization was categorized as linear programs and nonlinear programs. And nonlinear programs were hard, and linear programs were easy. That's not the right separation anymore. A lot of programs that are nonlinear, like the programs, the ones you just saw, in fact, the Weber point, that's not a linear program. Neither is least squares even. There are all these problems that are not linear, yet they're really easy. So while linear programming is no longer kind of the right distinction between easy and hard problems, it's still a very useful sort of useful formulation here that very used in practice. So this comes up all the time in a lot of practical problems here. And the idea is we want to minimize some function C transpose X. So that is in this case, linear function of X. It could be considered an we know it's convex because this is an affine function. You could add a constant term here, but that wouldn't matter because it wouldn't depend on X. So just drop that. So you just say minimize C transpose X, subject to some equality constraints. We have some constraints that AX equals B, and some inequality constraints. F of X is less than or equal to G. And I mean, when I say this for a set of inequality constraints here, these terms are both vectors. And so this inequality means element-wise inequality. It means every element in this vector is less than the corresponding element of that vector. One quick comment. You may have seen this before, these same problems, written with the formula here as just X is greater than or equal to 0. So without sort of these complex linear inequalities here, just with one linear inequality that just says X is greater than or equal to 0 as the inequality term here. It turns out those are actually equivalent. Can anyone guess why they might be equivalent? It's not obvious. And I'll drop that if no one chimes in quickly. But yeah. Oh, sorry. Yes.
You remove a different variable within fx minus y.
OK, right. So basically, you set some other variable y to be equal to fx minus g. And this one now, actually the other way around, right? G minus f of x. So this is an equality constraint too. And now this one has to be greater than or equal to 0. What do you do with the x's, though? I mean, x's, I'm writing this as everything has to be greater than 0. What about the x's? If you don't want to make them greater than 0, what do you do? What constraint would that be? What was that?
X greater than 0.
So yeah, so the way it's usually written is x greater than or equal to 0. But say you don't want that. Say you want x to be actually a free variable. You're sort of forced in a lot of, so what I'm saying is when you run a piece of code that will solve a linear program, oftentimes they will require that all your variables be positive. That's just the form of the program you solve. So how could you solve the same thing and not require some of them to be positive? Anyone? Minus the smallest one? So that's kind of tricky because how do you know what's the smallest one, right? I mean, until you solved it, you don't know which one's the smallest, right? So squaring is tough, right? Because squaring, when you have equality constraints here that you want to hold, it's tough to sort of square them. And then they become nonlinear equalities, which are really hard. This is a minor point, so we're not going to dwell on it. What you do is you separate variables into, for every x, you have two variables, one which represents the positive part of x and one the negative part of x. Those are all positive, and then your new equation here essentially becomes a times the positive part minus the negative part, and that's the same thing. If you didn't catch that, don't worry. This is a really, really minor point, but just if you come across something like this with only x greater than 0, just know that you can solve it. It's not hard. OK, the next sort of item in the hierarchy are called quadratic programs. So we had linear programs, now we have quadratic programs. And the only difference here is that in addition to this linear term in the objective, you also have a quadratic term. Quadratic term is of the form x transpose times q times x. This problem is convex if and only if this matrix Q here is semi-definite. Okay, and we're not going to worry about verifying they are semi-definite right now. We'll just say that these problems are convex in that case. What turns out is that the Hessian of this objective here is actually equal to Q. The second derivatives are equal to Q. The matrix second derivatives are equal to Q. And so the condition for it being convex has to be the Hessian is positive definite or positive semi-definite. And so this also, in order for this to be a convex function, the Q has to be positive semi-definite. OK, so there are a lot more classes of problems. There are things there's one people may have heard of called semi-definite programs, which are actually, though it's hard to see, these are even a higher subset, as in quadratic programs and linear programs are both instances of semi-definite programs. We're not going to worry about that here. We're just going to move on. And suffice it to say, there are a lot of potential problems that can be cast as convex problems. And so methods for solving convex problems are very useful in practice. We're going to talk in a second about how you actually go about solving these. But first, I just want to highlight some points about non-convex problems. Okay, and I'm not going to really talk about these here because we're going to talk about a lot of these throughout the course. I mean, most search problems you come across are in fact non-convex. But I want to just highlight sort of what it means for a problem to be non-convex, and then talk about ways you can actually solve it. So not surprisingly, non-convex problems are everything that isn't convex, right? Everything else is non-convex. Namely, if you have a problem like this, where either the objective or any of the constraints are not convex, the whole problem is non-convex. If any of the equality terms are not affine, the whole problem is non-convex. Doesn't matter if all the rest of them are. If you have any term that does not obey the criteria of the convex problem, the whole problem is non-convex. Now, as I said at the very beginning, and as you might expect, there are two overall approaches to how you solve problems like this. And they go by the names local and global methods. So, as you might expect, these solve the problem either locally, which you can do sometimes. So we have our function here. This non-convex function I drew before. So we have non-convex function. If you want, and say that you have some starting point x, some initial guess for what the solution might be. And you start there. If you are happy to get to here, then you're happy with a local search method. You're looking at where you are, and you're finding some point that's sort of nearby that's better than where you started from, but which still may not be optimal. And if you're willing to do that, you can use a local search method, and typically, though not always, they have similar properties in terms of the computation to convex methods. Now, we can solve them relatively efficiently using a variety of methods, which I'll talk about in a second. I should also say, this assumes, though, this is sort of obviously the case for unconstrained problems. For problems that are constrained, when you have non-convex constraints, it could be that you just can't find any solution that even obeys the non-convex constraints. That in and of itself can be a hard problem. And kind of the terms to have in mind here, which I'm not going to highlight, I'm not going to emphasize too much, but the terms to kind of have in mind here are those same terms as those completeness and soundness properties, as we talked about with search, right? So if you can find a feasible solution, even for a non-convex problem, you would say the algorithm is sound, whereas if you can find the optimal solution, it's actually both sound and complete. Okay? But that's local methods. These things, they don't guarantee to find a solution, even if one exists. And they certainly don't guarantee to find the optimal solution. This is in contrast to global methods, which we will spend a lot of time talking about in the course, because things like search, or some search algorithms, are optimal global optimization methods. But these find the actual optimal solution. Now, in contrast, they typically, again, sometimes this is not the case, but typically they will have higher computational complexity to get there, say exponential complexity in the problem size. Just one point, both of these things are used a ton in practice. So it's not like one is used and one is not used here. These are both used a huge amount. All search, or a lot of search, is trying to do this. And a lot of sort of local methods for optimizing things like robot motion planning, say, where you can't describe it convexly. These things are non-convex, but you're sort of okay with a reasonable solution. Those are local methods. These are both very, very common in practice and very, very heavily used. Those are the same thing, I guess. Okay, one more thing that I want to just mention now, but we'll come back to it in a few lectures. This is a class of programs called integer programs. What these are the same as a linear program, except you also make the requirement that your variables have to actually be integers, not just any real valued number. They have to be integers. Now, just doing that makes this problem a lot harder. In fact, it makes it NP hard, this problem. Of course, the cool thing is, by combining intelligent search methods, which we'll talk about in a second, with convex methods for solving linear programs, you can come up with really good ways of solving these things that really elegantly combine kind of search algorithms on the one hand and convex methods on the other hand. Yes? Can definitely not solve all of them. It's NP hard. Yeah, so it's NP hard. That means you can't solve them. But a lot of problems are NP hard, and we still solve them anyway for a lot of realistic size problems. Yes, no, absolutely. Yeah, you can't solve all of them. They are as hard as any problem that we really care about solving, so they're tough to solve. And can be very hard to solve. And sometimes even reasonable ones you would like to solve, you still can't solve them. So you know, there's no magic bullet here, but the algorithms we develop with combining search and optimization can do a good job sometimes. And by the way, this is non-convex, because if you look at a set of integers, now here's 0 and here's 1, a convex combination of those two things is not within that set, right? You have points in the middle. They're not within that set. So therefore, the set of all integers is not a convex set. OK, so now let's get to the final thing. And hopefully, we'll get through this all. But as I said, again, if we have to put a few to next time, it's fine. So now the question is, all right, I've told you how to formulate these problems. I told you that they are easy to solve. How do you actually solve them? So I'm going to go through a few things here, and this is going to be very fast. There are entire courses, as I say, devoted to this sort of content in these next few slides, obviously in a lot more detail. But I want to give you some basic intuition about the types of algorithms people apply to actually solve these things. If you have a problem, what do you actually do? So let's start with the unconstrained case. So we have just an objective value, sorry, an objective function. And you want to find, and we'll even assume it's well, I think I say 4 convex problems here. We'll have in mind a convex problem, though, a convex function, though actually some of these things will work in some cases when it's not convex too. OK. So we have a function f of x. We want to find a minimum point. Now, the minimum point, one thing that we know about this minimum point is that the derivative, think of a scalar function for now, the derivative of this function at the optimum point, so here's f of x, we know that the derivative, f prime at the optimum point is equal to 0. Right? And that's the case because the optimum point, the slope here has to be 0, or there would be a nearby point that was better. And in fact, for convex functions, we can even say this is a condition sufficient to make this the global minimum. We know it's a minimum and not say a maximum because convex functions can't have sort of these local maxima, right? So something like this would also be a point with 0 derivative, which is a maximum, but this is not a convex function. And in fact, if you remember from calculus, the way you sort of check to see if you're at a minimum or a maximum is you check the second derivative, right? You check the value of the second derivative. That will tell you whether you're sort of at a minimum, maximum, or like these inflection points too can also happen. But for convex functions, it's easy, right? Because we know the second derivative is always positive. So we're always, if we're at a 0, we're always at a minimum, never at a maximum. In fact, in the unbounded case, unconstrained cases, problems, they won't have maximum. They'll go on to infinity. All right, so that's for a 1D case. Now, in the case of a vector input function, we again, just like we did for the second derivative, we want to have an extension of this condition to functions that are functions of vector inputs. All right, and the equivalent condition here is that this other quantity called the gradient, and it looks, notation is very similar to the Hessian, just without that squared there. That should sort of remind you that this is the kind of analog of the first derivative, whereas the Hessian is the analog of the second derivative. This quantity here is called the gradient of a function, and it's just, so for a function f of x, which is Rn to R, this gradient is going to be a vector in Rn. So this, always think of this as a vector, just like you always think of the Hessian as a matrix. This is a vector in Rn where the ith element of this thing is just equal to the partial derivative of f of x with respect to xi. Okay? It's called the gradient of a function. And perhaps not surprisingly, the analogous condition for the gradient is that a convex function is at its minimum when the gradient is equal to 0. That means all the elements, all these derivatives are equal to 0. And importantly, this is only required and only sufficient. I guess it's sufficient no matter what, but it's only necessary if this is we're still talking about unconstrained optimization here. Okay? Just unconstrained. This whole first bit's going to be about unconstrained problems. Who's here seen this notation, like gradients, before? Okay, so some. Again, this class is not, we're not going to do sort of complex manipulations with these things, but just know this is kind of the analog of the first derivative for vector input functions. Multivariate functions. Column 2. Okay. All right, so now the question is, well, how do we know that in order to find a minimum of this function, to optimize it, we want to find some point, I guess I'll write it like this, some point f of x star, so that thing equals 0. How do we find that? You can do it a few different ways. First of all, sometimes, and sometimes it's a very rare case, but sometimes happens, you can actually compute what the gradient is analytically. Again, we're not going to worry about sort of the rules here. I'm just going to tell you this one rule. You don't have to worry about sort of general rules, for this class at least. But I will tell you that, for example, for a quadratic function, for f of x being equal to x transpose qx plus r transpose x, for that function, the gradient at any point x is just given by 2qx plus r. The analog here is if f of x were scalar and equal to ax squared plus bx, right? The first derivative would be equal to 2ax plus b. And the analog for a gradient and for a multivariate function is that you have this matrix expression here. Now, what you can do is you just set that equal to 0, and that will only occur if x star is equal to q inverse 1/2, actually, q inverse times r. That's great. That's the solution. That is the global optimum of this function. Yeah?
What if your objective function is piecewise, so you don't have a defined gradient?
Yeah, that's a great question. So the way we'll typically define piecewise functions is two answers to your question. The first answer is that you can define a generalization of the gradient called a subgradient, and as long, which is sort of like the gradient, but for something like this, you know, sort of any point here is the gradient, so really any point here could be a subgradient or rather, sorry, any line here could be a subgradient. And as long as 0 is within that subdifferential, it's called, that's an optimal point. That's sort of the mathy answer. The practical answer is that the way these are actually solved by a lot of systems is you transform it to a smooth problem, but one with constraints. So you encode those non-differentiable portions as constraints. If it's not quite clear how you do that, we can chat more. There's a lot of ways you can do that. And then you can actually use techniques from constrained optimization of smooth functions to still solve it. So for example, if you have a function that's always, maybe I'll actually pause on describing that too much because we don't have too much time left. But there are ways you can do it to solve these practically. But there's both the math answer and then there's also the sort of practical solution for the most part answer. And that you couldn't do this. You can't do this sort of stuff. Any of this stuff actually does not apply to that. So I probably should have called this unconstrained smooth optimization because it really is only applying to the smooth case. Those similar algorithms can work in the, not this one, but similar algorithms can work for the non-smooth case as well. Or non-differentiable case. Okay, another way you can do this, sort of find these things, is it's great that you can solve that one problem, and that is about the one problem you can solve that way. That function is pretty much an exhaustive list of the functions you can solve. Not quite. There's a couple more, but there aren't very many. So we oftentimes, if we write out what this, essentially what happens is if you write out what this gradient is, you can do it analytically. You can certainly sort of write out what these things are, given knowledge of the function, but you can't analytically solve that and set that to be equal to 0. This ends up being a nonlinear equation, and you can't solve it, at least not directly. Okay, so we have to have some other ways of solving these problems instead. One of the most common ones is a method called gradient descent. The idea is, what the gradient really does, and I'm showing here f prime of x0, so x0 is some point on this function here. F prime of x0 is actually be the slope of this line, right? That's the 1D analog. And what the gradient does is kind of point you downhill, or actually the negative gradient, right? So this here is positive. In that case, negative, so this is a positive function, and so negative this thing would point you this way. Similarly here, this is a negative function, so positive, the negative function would point you this way. Essentially, the negative gradient points you in the direction where the function is decreasing. Okay? And it actually points you in the direction where the function is decreasing sort of in the steepest manner. In 1D, that's kind of boring because it's either that way or that way. And you know by the sign of the gradient which way it's pointing you. But for multivariate functions, this is actually quite a bit more complex. You can sort of look, even for 2D, right? You have to sort of look 360 degrees around you and see which is the steepest direction. Well, it actually turns out the gradient gives you that direction. The gradient, again, actually it's the negative gradient. The gradient points you in the steepest increasing direction. The negative gradient points you in the direction of the steepest decrease. So the algorithm then that people will use is they will just take their current guess of x and subtract some small multiple of the gradient with the hope that that will put you closer to the solution. And this works, again, under some assumptions. If this term alpha here, which is called the step size, is too big, then you can actually bounce around, right? If gradient descent would sort of take you a step this way in this thing, but if you take a step this big, you're sort of, then you're even bigger and you sort of will bounce around a lot. But for the properly chosen step size, you will actually get a solution. It actually is even the case even for non-differentiable functions. So even for functions that have no gradient at a point, if you replace the gradient here with a subgradient and have a certain way of decreasing your step sizes as you get closer to the optimum, that actually also will solve the problem. So this works not just for smooth functions, or it's not just for differentiable functions, but actually for non-differentiable ones too. Sort of impressively. That's sort of actually surprising. But you need more math for the non-differentiable case. This is very, very common, by the way. And in fact, because it's such a simple algorithm, a lot of very large-scale methods like machine learning or large-scale optimization are actually moving back towards simple gradient methods for solving these things. All right, the last one is called Newton's method. Actually, who here has heard of Newton's method before? In the 1D case or in the multivariate case? Who's heard in the multivariate case by a show of hands? Okay, so not nearly as many, which is actually a good thing. Newton's method says, okay, the condition we're trying to solve is setting this gradient to be equal to 0. Okay, that's what we want to optimize a function. What Newton's method does is Newton's method is called a root finding algorithm. It finds points of a function that are equal to 0. So Newton's method, when I say Newton's method for optimization, what I mean is we're going to apply the root finding Newton's method to the derivative of a function to find a point where that derivative is equal to 0. And I won't really bother about the exact form of what this takes. Essentially, what it's equivalent to is Newton's method kind of works by fitting a line to the function first and finding the 0 of that line and repeating this process, if you remember right from calculus. This thing is virtually identical to that. But the final form of the algorithm just says, I'm going to take x, my current point. I'm going to subtract this term here. This term is the analog of this guy for root finding. It's just for the finding a 0 case. You take the Hessian of this function at that point. You invert that, multiply it by the gradient, and repeat this process. Subtract that from x and repeat the process. I'm doing this very, very briefly because I don't think it's, if we do use the method, we'll talk about it more when we use it. And we'll talk about it in the specific case that we're using it. This is a general method, and the important thing here to take home is just that this is another way of finding this point here where the gradient is equal to 0, using a little bit more complex way than just taking little small steps. The sort of practical side, too, is that it's more expensive to compute these iterations than it is to compute an iteration of gradient descent, right? Because you have to form this bigger matrix here and invert it. That's a lot more work than just forming this vector. But the advantage is that the steps you take are often a lot better. So you'll need many fewer steps than you do with gradient descent. And in fact, oftentimes you need very, very few steps to get very, very close, essentially as close as you can get on a computer to the optimum with Newton's method. Okay, so that covers unconstrained optimization, the 3 ways, right? You have direct solution, you have gradient descent, and you have Newton's method. Again, kind of blazing through all these things, just getting the high-level picture here. Now the question is, what about when you have constraints? Now we're going to put the constraints back in. That was all for unconstrained optimization. And for constrained optimization, there are actually now a few things you can do. There are a lot more things than this you can do, by the way, but there are a few things you can do. One of the simplest methods is if you can come up with what's called a projection operator. This is an operator that takes any point and projects onto the feasible set. So for example, if your feasible set is the set of all points where x is greater than or equal to 0, so you want to minimize, say, f of x. I'm going to be pedantic here. Minimize x subject to x greater than or equal to 0. I can find a way to project onto this set. So given any point, I can find, in some sense, the closest point. This is any point in an Rn, so some can be negative. I can find the closest point that lies within that set. And closest measured here by really, actually, in this case, any distance you could define would have this be the closest point. That point is just you take all the negative entries and you just set them equal to 0. So every entry is equal to the projection operator is equal to the max of x and 0. Now you can't always do that. Okay, it's actually sometimes very hard to find a projection operator. So for example, if I had actually a linear program here, or I guess a linear program, if this was a just a linear term here. Now my constraint set is this thing. And actually projecting onto this set is just as hard as solving the original problem. So it doesn't really help you, right? You can't actually come up with a projection operator that's very good, because it's a hard thing to project onto. But if you can find this projection operator easily, like you could say if you're just worried about optimizing some function subject to only this constraint, then the following algorithm called projected gradient descent, called projected gradient descent will work. It's exactly like gradient descent. You take your current x, subtract off some multiple of the gradient, but then you project that back into the feasible set. Okay, you apply your projection operator to that whole thing. So x here at every iteration is always feasible because it's always, it's always some projection onto the feasible set of some other of this thing. Okay? So can't always do this, but when you can do it, it can be very efficient because you just need to write, one more line of code in your gradient method. You just say, and take this thing and project it onto the feasible set. But again, not always possible to do that easily. And the last thing I want to mention is something called a barrier method. So this is actually how some of the most complex, I shouldn't say most complex. This is actually how some of the most powerful solvers there are work. It's a very, very simple idea. What you do, and I'm just going to talk about inequality constraints now. You have to handle equality constraints a little bit differently. But what you do is you have your function here, minimizing this subject to all these gi's, gi of x, that's equal to 0. And what you do is you transform this problem into an unconstrained problem. Right? And you do that by taking the log of the negative of these constraints. So these have to be all less than 0. So that means the negative has to be greater than 0. The log is infinite if this thing, so this term here, log of negative g of x, would be infinite if any of these terms was greater than 0, or greater than or equal to 0, actually. Okay? So this, if you solve this thing, you cannot have any of these things being greater than 0, or the objective would be infinite. The log is actually negative infinity, but we're taking the negative log here, so that would be infinite, positive infinity, if any of them are bigger than 0. Is what always positive? T. Yes, t. Yes, t is always positive, yeah. Otherwise, it's not convex anymore. You're subtracting a positive, subtracting a convex function then. Okay, so now the interesting thing is, the problem though, of course, is that for t being strictly positive, this is not the same solution that you get to these things as you would get to the original problem, right? You have more terms than this. The original problem just tries to minimize this. So what these algorithms do is they actually sort of schedule a t getting smaller and smaller that will get you closer and closer to the solution. And this is really tricky to do well in practice, I should say. Because when you start having t very small, you start running into floating point precision errors on your computer, which is a bad thing. To do this kind of in a proper way, you have to be very, very careful about how much you decrease t every iteration. You have to solve it very exactly for every given t, and do this kind of in a very, very smooth manner. And if you use something like Newton's method to actually solve these unconstrained problems, this is actually called something called a interior point barrier method, which are, as I say, sort of the state of the art a lot of times in solving large, complex, convex problems. I have 3 more slides, which we'll go over in the beginning of the class next time. And they are actually the ones that are most relevant to you for this course, because they are the ones that talk about how you will actually solve these. You will not implement these algorithms. They are very complex. They are very hard to implement. You will instead use libraries that can solve these things pretty well, such that you can solve problems like this in a few lines of Python code. So we'll cover that next time. The slides are online too if you want to preview, but we'll cover that at the beginning of class next time and then go to more search.